Okay, last section of this chapter is on the second law of thermodynamics. So let's look at this situation first. The high cost of gasoline and environmental issues associated with internal combustion engines are important issues. A partial solution to these problems would be more efficient engines. So what does the term efficiency mean when applied to an engine? Think about how would you define efficiency? And how efficient do you think present engines are when given as a percentage? Take your guess. Can the efficiency be improved? If so, how? So here's an heat engine. We have work out is equal to the heat. Remember, Q is heat. What's added minus what's released. So the heat added minus heat expelled. Efficiency measures the work out as a fraction of the heat added. So supposing 100 joules of heat entered the engine and it does 35 joules of work, how efficient is the engine? We would take 35 divided by 100. It gives us 35% efficient. So if we want to calculate just the efficiency, you can take the net work done by the engine, which is energy added minus energy removed, and then divide that by the energy added to it as heat. To find the percentage, you take energy removed as heat minus energy added as heat. So the second law of thermodynamics, so if efficiency were equal to 1, or if it was 100% efficient, that only happens if the heat in minus heat out is 0. Like the amount of energy you put in is the exact amount of energy that comes out. All the heat input is converted to work. The law of thermodynamics requires some heat output for all cyclic processes, so no such engine exists. You cannot have a 100% efficient engine. And that is what the second law of thermodynamics is based on, that no cyclic process that converts heat entirely into work is possible. So let's try this problem. If a steam engine takes in 198 times 10 to the third joules and exhausts 149 times 10 to the third joules as heat per cycle, how much work is being done? Well, work where the heat that's put in minus the heat removed, so we'd have 198 times 10 to the third minus 149 times 10 to the third joules for each joules. So that should give us, whoops, oh, we need to find efficiency. Let's find the answers. 49 times 10 to the third joules. And then efficiency, we would calculate efficiency by what's 149, what's given out, times 10 to the third over what's added. We put in 198 times 10 to the third. And that would give us 24%. These are some different types of engines and how efficient they are. Okay, so you can compare those types of engines. Friction and heat loss through conduction lower the maximum value of the measured values. So that's where some of that efficiency is lost. Entropy provides another way to look at the second law of thermodynamics. Entropy is a measure of disorder or randomness in a system. So more disorder implies greater entropy. And steam has more entropy than water because the molecules in steam are moving more randomly and faster than water molecules. Hot air has more entropy than cold air. So which gas shown above will be more effective when doing work on the piston? The gas on the left, because all these molecules are moving in the same direction, they're all going to transfer their energy to the piston, whereas in this case, some of them are hitting the sides of the container, some of them are hitting the piston, so it's not as efficient. Which is the most likely arrangement of the molecules? What's probably happening in a piston? This is more likely. This is what real gases would behave like, they aren't all going to hit the piston at the same time. So we have higher entropy in the right because it's more disorganized. So an equivalent version of the second law of dynamics is this. In a naturally occurring processes, the entropy of the universe increases. So you're always increasing. Processes naturally go from more orderly to disordered. A tendency towards disorder is related to the waste heat in the heat engines. So imagine an experiment in which water is left outside to freeze. What happens to the entropy of the water during the freezing process? Now the water itself is liquid here and then freezes, so it actually becomes more orderly. But what happens to the entropy of the air? The air is starting this with this much disorder, and the speed has increased because the heat from the water has gone into the air. And so the air becomes more disordered, and it actually becomes more disordered than the water becoming ordered. So overall, the increase for the air is greater, so the decrease for water, so entropy increases.
Entropy is a measure of a system's disorder. An orchard is an example of a well-ordered system. Walking through an orchard, you would notice that the trees are equally spaced, and your natural conclusion would be that someone planted the trees. In a forest, trees are randomly spaced. This is an example of a fairly disordered system. The second law of thermodynamics can be expressed in several ways. One way to express it is in terms of entropy change. The entropy of the universe increases in all natural processes. Imagine the following situation. It's been quite a while since you straightened your room, and you are getting frustrated by the mess. You decide it's time to create order in your room. You put the dirty clothes in the laundry basket, clean clothes in the closet, shoes in their boxes, books and magazines in the bookcase. Soon, your room becomes a space with well-ordered things. You might think that this is a violation of the second law of thermodynamics. The entropy of your room has decreased, not increased. It is true that the entropy of your room has decreased, but you might be forgetting that you were inside your room doing work. The entropy of the room has decreased, but the entropy in your body and the room's air has increased. You used energy to straighten up your room, energy that you got by burning fat in your body. The burning converted well-organized fat molecules into disorganized waste products such as the carbon dioxide you exhaled and the heat transferred from your body to the room's air. So the entropy of the system as a whole, your room and you, increased. This is true for any natural process in any system in the universe. Entropy can decrease for a part of the system. You have a neat room, provided the decrease is offset by a greater increase in entropy elsewhere in the system. In this case, your body.